Yes, Assalamu alaikum. So in the last class, we were discussing about the formulation of DC load flow problem. So we started the discussion of the DC load flow solution uh, by introducing or by revisiting the AC load flow analysis problem. And what we did actually, we adopted some assumptions, simplifying assumptions, which led us to the DC load flow formulation. So if we just go through quickly what we discussed in the last class in the DC load flow part of our discussion, we talked about the power injection at any bus I. So if it is an AC load flow problem, so usually we talk about the real power injection at bus I, which is basically the real power generation at that bus minus any demand supplied or any demand required to be supplied at that bus. Similarly, we can formulate the expression of the reactive power injection at any bus I. And that is again a function of the generation of reactive power by the generator present at that bus minus the reactive power demand at that bus. Then we looked into the expression of the current phasor II, which is basically the apparent power, conjugate of the apparent power divided by the voltage phasor at that bus, conjugate of that bus. And then we talked about the injected current vector, where if we have n number of buses present in the power system, then there will be I bus array or vector, where the dimension of I bus would be simply n bus by 1. And that I bus is simply the multiplication of can be obtained. The I bus vector can be obtained by the multiplication of the Y bus matrix, whose dimension is n bus by n bus, multiplied by the V bus vector, again, whose dimension is n bus by 1. Then if we expand this expression, instead of writing the I bus as a vector or as an array, if I'm interested in finding the expression of I injected at a certain bus, then I can take help of these two matrices and vectors, and I can pick the relevant entries of the Y bus as well as the relevant entries of the V bus. And accordingly, I can write the I injection as a summation of the multiplication of these two vectors. So these things were discussed in the last class. I'm just revisiting those things. Again, the complex power injected at bus I is simply the VI phasor and II phasor conjugate. So VI phasor, if it remains as this, as it is in the phasor form, whereas the II conjugate, if we have the II expression, phasor expression, then we can take the conjugate of the whole expression and then we can simplify it. And finally, we come up with this expression, where we have the presence of the ith bus voltage magnitude, the jth bus voltage magnitude, the Y bus admittance entries, magnitude of that, and the associated angles will come into play. And again, we can find the expression of the real power injection at the ith bus, whose expression is this, and similarly the reactive power injection at the ith bus, which is QI. And these two are simply taken from this whole expression, where this expression is in polar form, and we can expand it using the Euler's identity. And then, we can express this into rectangular form. So this whole expression can be expressed like some real part plus J into the corresponding imaginary part. So the real part of this complex power will give us the real power expression, whereas the imaginary part of this complex power expression will lead us to the reactive power expression. So ultimately, we get these two expressions. And then we said that because of the presence of the sine and cosine terms, these two equations are nonlinear in nature, and that's why the AC load flow problem cannot be solved analytically. Rather, we have to adopt some numerical techniques. The most popular techniques for solving the AC load flow are the Gauss-Seidel method, the Newton-Raphson method, or the fast decoupled method. Of course, other than this, there are also some other methods which can be adopted. Then the line flow expressions was provided as Sij phasor equals to VI phasor into IIJ conjugate. And then VI is kept as it is, and the IIJ, which is basically the line flow between bus I and bus J, we take the conjugate of that. So simply it is S equals VI conjugate. And IIJ can be represented by the bus voltage phasor I minus bus voltage phasor J divided by the reactive part of the impedance. Okay, considering the fact that we are ignoring the resistive part of the lines. And then if we simplify this, finally, we can also find out the reactive power flow through the line between bus I and bus J, and real power flow through the line between bus I and bus J. And then we had the assumptions of the DC load flow. Once we adopted all these assumptions, we came up with the expressions presented in equation 1 up to equation 4, which is summarized here. Okay, so in the DC load flow formulation, we can say that for an N-bus system, the bus voltage angle of the swing bus is known. Of course, the swing bus is taken as the reference bus, and accordingly, the angle of the reference bus phasor, voltage phasor, is taken as 0. And that will remain unchanged, okay, throughout our solution. The swing bus or the reference bus voltage angle will be set at 0 throughout the solution. So the number of unknowns for the DC load flow actually becomes equal to N bus minus 1. And these N bus minus 1 are simply the theta variables. So let's say if we have a 3-bus system, just for an example, if we have a 3-bus system, and among these 3 buses, we have one bus, let's say bus 1, bus 2, and bus 3. This bus is the slack bus or the reference bus. So the theta for this bus, theta 1, is set to 0, and that will remain constant. So the only unknowns are theta 2 and theta 3. So the number of unknowns is simply 3 minus 1, which is in general N bus minus 1. Why theta 2 and theta 3 are the only unknowns? We discussed it in the last class, because if we look into the expressions of the Pij and Qij, these are the line flows, and similarly the expression of Pi and Qi, okay, the injection. Okay, the injection will come later on. So let us take this one first. Okay, so Pij and Qij expressions. You can see that in the DC load flow formulation, we assume that Vi and Vj, all the bus voltage magnitudes are assumed to be equal to 1 and unchanged throughout the solution. So this will become 1. This will also become 1. Another assumption we said that theta I minus theta j, these adjacent bus bus voltage angles are very near to each other. So thus the theta I minus theta j value, this is very small, approximately equal to 0. And sine of very small angle is basically sine of theta I minus theta j can be approximated as theta I minus theta j. So ultimately this becomes what? Ultimately Pij becomes 1 into 1. So this is 1. This is 1. Sine theta I minus theta j is simply theta I minus theta j divided by the line reactance Xij. So simply the line flows can be represented as a function of theta I and theta j, okay, function of thetas, bus voltage angles, whereas the denominator is simply the line data, can be found from the line data. This is basically the line reactance. So this is Pij after application of the assumptions associated with the DC load flow. What about Qij? Qij is simply 1 squared. This is 1 squared minus 1 into 1. So this is 1. This is again 1. This is 1. And cosine theta I minus theta j, as theta I minus theta j is very small, so cosine of that is approximated equal to 1. So you see 1. So all these are 1 divided by Xij here. So this will become 1 minus 1 equals to 0. So there is no Qij basically, the DC load flow. So means no reactive power flows through the lines or through the network in a DC load flow problem. So you see that the line flows, basically the real power flows, these are functions of theta. So once we know theta, this is already known. Once we know the theta, we can find out Pij. So theta are unknowns. Okay. So theta are the unknowns. What about the injection? Okay, so the injection of Pi and Qi, let's go into that expression again. So we are done with the power flow, real power flow and reactive power flow from bus I to bus J, which are also treated as the line flow. Now come to the injection at a bus, real power injection and reactive power injection. So if I start from the AC power injection expression. So this is nothing but Vi, summation of Vi, Vj, Yij, cosine of theta I minus theta j minus delta ij. Okay, j equal to 1 to n bus. So this is the expression. Now, if I apply the simplifying assumptions associated with the DC load flow, I can write it as summation. Vi is 1, Vj is 1, magnitude of Yij. Okay, so magnitude of Yij. Yij is simply, in general, the magnitude is Gij square plus Bij squared. But as we have ignored the resistive part, so this will become 0. This will not appear here. So we get Bij squared. So this is basically Bij. Okay, this is basically Bij. So Yij can be written as Bij, the magnitude of the susceptance or the susceptance entries of the Y bus matrix, basically. Then cosine theta I minus theta j is a very small angle. Okay, delta ij, because delta ij is the admittance angle. Okay? Because our real part of the admittance is negligible, so we can write that Yij equals j of phasor Yij is j Bij. So I can write Yij equals Bij as the magnitude, angle 90. So j is transformed into the angle 90 degrees. So this is basically 90 degree because of this, r is very, very less than, r is very, very less than x, the line. So thus this becomes 90. So cosine some theta angle minus 90 will make it sine theta I minus theta j. Okay, so finally we have this Bij theta I minus theta j. Again, we can see from the expression that because Bij is again the entries of the Y taken from the entries of the Y bus matrix. So these are constant as long as the network structure or network topology is not changed, the power system network topology is not changed, Bij will remain constant. Theta I minus theta j, these are the unknowns again. So we see that for Pij here, theta I and theta j are unknowns. For Pi, theta I and theta j are unknown. So in general, again, for the Qi, there is no presence of theta I, theta j. This is simply a constant. So Qi is a function of Bij's, whereas Qij, the line reactive power flow, are 0. So overall, if I consider equation 1 to equation 4, our unknowns are the thetas. Okay? Thetas are the unknowns. So this is why we were saying that if we can find out theta, all the thetas, then we are done with the DC load flow solution. Once we find out the theta, these theta will help us to find out the real power flow through the lines, the real power injection. Okay, and these are the things that we require to find with the help of DC load flow. Because reactive power flow through the line is 0, and reactive power injection can be found from the entries of the Y bus matrix. So thus the thetas are the unknowns. The thetas are the unknowns. So unknowns are the thetas. Now, how many thetas will be there? Remember, theta is the bus voltage angle. Bus voltage. These are the bus voltage angles. So if we have n number of bus in the system, so we should have theta n bus number of unknowns. Okay, now among all these n bus, one of the buses is slack bus, and the remainings are the n bus minus 1, right? So because the slack bus theta is known, so theta slack is known, and that is our reference bus, so that is 0. The remaining n bus minus 1 entries will be the unknowns. So that's why we said that the unknown number of unknown variables for the DC load flow are simply n bus minus 1. So this is the explanation for that statement. So this is the explanation of this. Thus, the number of unknowns for the DC load flow becomes equal to n bus minus 1. Now, once we know the remaining bus voltage angles, means other than the swing bus voltage angle, because that is already known, if through the solution of DC load flow algorithm, we can find the remaining bus voltage angles, then we can find the other unknowns like real power injection at a bus, that is PI, real power flow through the lines, those are PIJ, and those can be obtained with the help of these equations 1 and equation 3, which are shown in this slide, okay, slide number 8. Equation 1 will give us the real power injection. Equation 3 will give us the real power flow through the lines. Okay, so then what we did, we tried to formulate the DC load flow problem for a sample 3-bus system. And what we did, we actually wrote down the P injection expressions. Okay, so P injection expression, we have got the generalized expression for PI. So now we can take note of that, and we can apply that knowledge to find out the real power injection at, let's say we have 3-bus system. So for these 3 buses, if we want to find out the PIs, so what is the general expressions? What is the general expression of P injection? It is simply J equals 1 to n bus Bij theta I minus theta j. And we also said that here J is not equal to I. Because we can clearly see that J is not equal to I, because once J is equal to I, then theta j becomes equal to theta I, and ultimately these two will be cancelled, and there will be no contribution of this entry like Bii theta I minus theta I. So when theta I is equal to J, your entry here in the summation, in this series of summation, your entry will be like this: Bii theta I minus theta I. So ultimately it will be 0. So you can write it like this. So if I am looking for P1, then I start from, so P1 means I'm looking for the summation from J equal to 1 to n bus. So because I here is equal to 1, so J cannot be equal to 1. So I have to start from B1, 2. So J will start from 2 up to n bus. For a 3-bus system, n bus is 3. So I have to write it like this: B I is 1. So I cannot be equal to J, or J cannot be equal to 1. So it cannot be B11, because if it is B11, then ultimately this thing will return 0. So there is actually no outcome of that. So J will be starting from 2 to n bus. That means 2 from 2 to 3. So it will be B12 theta 1, because I remains 1, minus theta 2, plus then J becomes equal to 3. So B13 theta 1 minus theta j is theta 3. So this is the expression of P1, which is shown here. Then we grouped it. We grouped the coefficients of theta 1 and theta 3 and theta 2 as well. So these are the coefficients. So the same expression is simply rewritten in the form of coefficients of thetas. Similarly, for P2, we do the same. So for P2, I cannot be equal to J. So that means when I is 2 here, there won't be any B22. Okay, so B22 term will actually return nothing. So if we write it like this, B22 theta 2 minus theta 2, we can write if we want, but ultimately this will give 0. So that's why the remaining 2 entries are there for the summation. For this summation, we have B21 theta 2 minus theta 1, where I now here is 2, plus B23 theta 2 minus theta 3, and the remaining part is 0. Again, we group the coefficients like this, and we do the same thing for P3. And finally, again, we regroup, we rearrange this expression, and we pick up the coefficients for theta 1, theta 2, and theta 3. Now, these three expressions, simply we have written in the matrix form. So we have on the left-hand side, 3 elements of the vector P or P injection. So this is our, we can write P injection vector of 3 elements, where 3 is the number of bus. So P1, P2, P3, the unknowns on the right-hand side are thetas. So these are the unknowns, bus voltage angles, and the remaining thing are the coefficients. So simply we pick the coefficients and fill up the space, fill up the blanks. Now, in the last class, we also mentioned how we are going to get these entries. These entries can be easily obtained with from the knowledge of Y bus. Okay, but there is other way around, another way. So let me explain it today. One way I discussed in the last class, that is with the help of Y bus, we have to first form the Y bus matrix, and then using the entries of this Y bus, we have to formulate these B matrix there. Another way to formulate this B matrix is this. So here, if I consider these as our B matrix for today's lecture, so let's say this is the B matrix. What is the dimension of B matrix? It is simply 3 by 3. So the dimension is n bus, number of row is n bus, and number of columns is also n bus. So that is n bus by n bus. Now so these entries are what? This is my B11, this is B12, and this is B13. Okay. Element wise, this is B11 entry, B12 entry, and B13 entry. Now, how am I going to calculate this? Let us see. So B11 is simply the summation of reactances. We will use the reactance elements, and we will take the inverse of that. That is the susceptance. Remember, B entries are like simply the susceptance of the lines. So when it is self-susceptance, I have to write it like this: 1 upon x12 plus 1 upon x13, considering the fact that my network looks like this. So let me draw the network, which will actually appear later on. In one of the later slides, the network will appear. So I am drawing the network here. So you have 2 bus. You have 2 buses like this with the generators. And another bus will be like this, where we have the demand. So let's say we have the network connection like this. We have 2 generators and the demand here. Let me check the network first, so that exactly what I'm looking for. Yeah. So we have load at bus 2 and bus 3, and generation at bus 1 and bus 2. So there is a load at bus 2 and bus 3. And there is generator at bus 1. So this is bus 1, this is bus 2, this is bus 3. Generator at bus 1, generator at bus 2, load at bus 2, and load at bus 3. So this is the network. So now how am I going to calculate B11? So how many lines are originating from bus 1? There are 2 lines. And the first, let's say this is the first line. So one line is connected between bus 1 and bus 2, and the reactance is X12. Another line is connected between bus 1 and bus 3, so the reactance is X13. Another line is connecting bus 2 and bus 3, so this is reactance X23. So how am I going to calculate B11? Simply, I have to take the inverse of the reactance of those lines which are originating from bus number 1. Okay? That is B11, self-susceptance entry. So which are the elements? X12. So I take 1 upon X12 because that is the susceptance. And I take another line, X13. So I take inverse of that, 1 upon X13. And there are no other lines. So these are the 2 lines that are connected to bus number 1. So I take all the line susceptances that are originating from bus number 1. So this is how I am going to calculate B11. Then what is B12? B12 is simply I have to take that line which is present between bus 1 and bus 2, which is this line. And then I have to take a minus, and I have to take the inverse of the reactance of this line. So simply this is B12. So these are off diagonal entries. This is diagonal entry. These are off diagonal entry. Luckily, this B matrix over here is symmetric in nature. Means once I know B12, I can also say that that is same as B21. So the magnitude of this and magnitude of this along with the sign will be exactly the same because of the symmetric nature of this bus. Then what will be B13? I have to look at the connection between bus 1 and bus 3, the corresponding reactance, take the inverse of that and put a minus sign. So that is your B13. And due to symmetry, this will be the same as B31. Okay. Then we have B22. So again, for B22, what I have to do, I have to look at bus number 2 and I have to look at those lines which are originating from bus number 2. Again, there are 2 lines. Okay. So 2 lines, one line is between bus 1 and bus 2. So simply I have to take the inverse of that line reactance. Another line between bus 2 and bus 3. So I have to take this one. And there are no other lines, only 2 lines. Okay, this is one line, this is another line. So that is the expression of B22, this entry. Then what is B23? I hope by now you should be able to answer the B23 expression. So B23 is simply, I have to look between bus 2 and bus 3. There is a line, and I have to take a minus sign and take the inverse of the line reactance present between bus 2 and bus 3. So that is B23. And due to symmetry, the off-diagonal entry will be the same. So that will be the same as B32. The last entry remaining is B33. Again, I have to look at bus number 3, and I have to look at how many lines or which lines are actually originating from this bus. So these are the 2 lines. I take all the summation of all the line reactances, inverse of the line reactances actually. So 1 upon X13 plus 1 upon X23. So this is how we can also formulate this B matrix over here, okay, without the requirement of calculating the Y bus matrix. Okay, directly I can calculate this B bus. I hope it is clear. So now, once we have the B matrix, then we can complete our entries for a given network data, given line data. We can calculate all these B's. Okay, and once we do that, then we can solve for the P injections if we know the theta, right? But the question is, do we need the theta till now? The answer is no. Thetas are basically our unknowns for the DC load flow problem. So first of all, we have to find a way to find out the thetas. And with the help of those theta, and with the help of these B matrix entries, we can then find out our P injection. The question is how to find out the theta. So to find out the theta, if we look closely at this vector here, we know already that, let's say bus number 1, if we assign it as the swing bus, so that is the corresponding theta angle should be 0. So only unknown is theta 2 and theta 3. So you have to only find out n bus minus 1 number of unknowns. So that is theta 2 and theta 3, 2 unknowns. Okay, so if we can find the values of theta 2 and theta 3, then we can use those values here, and accordingly we can find out the injections here. And that said, later on yesterday's class, we said that how we are going to find out, the last class, sorry. In the last class, we discussed about this thing that theta 0, theta 1 is known. So we don't have to solve for theta 1, theta 2, and theta 3. Rather, we have to solve only for theta 2 and theta 3. And accordingly, we can take a reduced dimension of B matrix. Okay. so that P1 is still not appearing here, no more appearing here. That means we are only concerned about this block. So this part and this part are no more considered for the time being. This is not considered, this is not considered, because this is actually known. So if we can find theta 2 and theta 3 just by taking it to the other side and inverting it, so simply we will have B22, which is basically this one, B23, which is this one, B32, which is the same as B23, and B33. So inverse of that, okay, inverse of that multiplied by P2, P3. Remember this one here is simply P injection. So that means that if I know the injection at bus 2 and the injection at bus 3, and I know, of course, these things because these are some function of the network elements, then I can find out theta 2 and theta 3, where this B matrix, B dash, I call it B dash. This is simply n bus minus 1 by n bus minus 1. The dimension is reduced by 1. And this is also n bus minus 1 by 1. And this is also n bus minus 1 by 1. So if I know B dash inverse, okay, I can take the inverse, and hopefully this is invertible. Once this is invertible, I can calculate the inverse matrix here. And if I know the injection, power injection here, I can calculate theta. And thus I can solve for the theta unknowns. And once I know that, then I can calculate the other P line flows and the remaining P injection. Remember, here P1 is still unknown. P1 is still unknown. We still don't know P1. Okay, that is the swing bus power generation. Swing bus power generation is still unknown. So once we know the thetas, then we can solve for power line flows, real line flow through the lines, and that will actually ultimately help us to find out the power injection, real power injection at the swing bus. So with this, let us move forward. Let's move forward. So this is what is mentioned over here. Once we know the theta, then that will help us to find out the line flows, okay, P12 and P13, according to the network that I just drew earlier, the 3-bus network. So we can find out P12 and P13. Once we know P12 and P13, and that will help us to find out P1. So let us apply this knowledge to a problem with some given data. And let us try and see how we can apply this knowledge to solve a DC load flow problem. Okay, so this thing, okay, before we start the example problem, we again focus here, okay, about the line flow. So this line flow, P12 and P13, this is for the 2 lines present in our system. But can we generalize these line flow expressions, okay? Can we generalize this? So for generalization, we can adopt this expression. So we can adopt this expression. So simply we can see that the line flows can be written as this, right? Line flow P12, what is P12? This color. The line flow over here, change, yeah. So the line flow here, as we talked about, is simply P12. If it is P12, then it is theta 1 minus theta 2 by x12. So theta 1 minus theta 2 by x12, okay. So to capture this expression, to represent this expression in matrix form, we can use this block, and this block. Where this block is nothing but the node arc admittance matrix A, node arc incidence matrix, which is simply the A matrix. This matrix over here is simply the B line, a diagonal matrix having only diagonal entries non-zero, and all the off-diagonal entries are 0. And this is the theta vector. And again, along this line, we have the buses, bus number increment. So it is bus 1, bus 2, bus 3. And along this line, we have, along this direction, we have the line entries. So here in this network, we have actually 3 buses, bus 1, bus 2, bus 3. So we have bus 1 entry, bus 2 entry, bus 3 entry. And we have also 3 lines. Okay, so bus line 1 entry, line 2 entry, and line 3 entry. So how to formulate it, discussed earlier for another network maybe. So here I am also again repeating for this network. So line 1, this is line 1, remember. For line 1, we have 2 buses connected. Sending end bus is bus number 1. So it will carry a +1 entry. Receiving end bus is -1. So it will carry a minus sign. Receiving end bus number 2. So it will carry a -1 entry. Bus number 3 is not connected with line 1 in any way. So that will carry a 0 entry. Line number 2, it is connecting bus. Okay, so they're considering this as line 1, this as line 2, and this as line 3. Okay. So line 2 is connecting bus 2 and bus 3. So let's say bus 2 is the sending end bus 3 is the receiving end bus. And line 3 is present between bus 1 and bus 3. Again, bus 1 is the sending end bus and bus 3 is the receiving end bus. And again, bus number 2 is not connected. Bus number 2 is not connected with line number 3 in any way. So it will carry a 0. So this is how we can form the node arc incidence matrix A. What about B line? B line is simply a diagonal matrix where the diagonal entries are simply obtained. The diagonal entries are simply obtained as the inverse of the line reactances. Okay. So this is the reactance of line number 1, x12. Okay. Line number 1, this is x12. Reactance of line number 2, x23. Reactance of line number 3, which is x13. So you simply take the inverse of that line reactance, corresponding line reactance, and you get you actually put them along the diagonal entries. And the remaining off diagonal entries are all 0. Whatever matrix you will get, that is known as B line. So B line into A matrix into theta. Okay. So in general, P line in per unit can be obtained by this expression, B line into A into theta. Okay. And of course, you can check this expression. You can check this expression that, and also other expressions, P13, P23, any expression you can check. P13 is what? Theta 1 minus theta 3 divided by x13, and P23 is theta 2 minus theta 3 by x23. You can check any of these 3 expressions that this expression, this generalized expression or matrix vector multiplication, this basically returns all these 3. Okay? You can check simply by multiplying these 3 matrices. And this is the expression that I just wrote here. B line, P line per unit is B line into A into theta, which is in per unit. If you want the actual unit, megawatt flow, you simply multiply this expression by the corresponding base power, base MVA. Okay? So you will get P line in megawatts. So now with all this information, probably we are in a position to solve the example problem. So let us move to the example problem and see how the DC load flow solution can be obtained. Okay, so the same 3-bus network we will actually use for our example demonstration. And here only what we have some data. Okay, so these are the data. So we have the same 3-bus system. Base apparent power is given over here. Bus data is given. So bus number 1 is considered to be the reference bus. Bus number 2, because of the presence of a generator, this is the PV bus. And bus number 3, there are no generators. So this is the PQ bus or load bus. Bus number 1, you see there are no demands given. Okay, no loads connected. So these are the load symbols, demand symbols. So there is no demand. So both PD and QD are 0. What about PG? PG is the unknown. Okay, PG you have to find out through the solution of your DC load flow. Bus number 2 specification. It is a PV bus. The demand here is given as 10 plus J5. Okay, 10 plus J5, PD plus JQD. PG is 63. So basically, this is providing us 63 injection. Okay, so power input to the bus, power injected to the bus is 63, and power taken out from the bus due to the presence of the load is 10 megawatt. So this is 63, this is 10 megawatt. What about this bus, bus number 3? There is no generator, so PG will be 0 actually. So there are no injections in the form of generation, but power is drawn out from this bus. How much power is drawn? Real power, it is 90 megawatt. So how can we formulate the expression of PI at bus 2? So P2 injected is P2 generated minus P2 demand. So what is P2 generated? 63 minus P2 demand is 10. So P2 injection real power is 53 megawatts. Similarly, P3 injection is P3 generation minus P3 demand. What is P3 generation? 0, because there are no generators, minus 90 megawatt, the demand. So it is minus 90 megawatt. Means 90 megawatt is actually taken out from this bus. So these are the injected power. What about P1I? This is unknown. This we still don't know. We have to solve for it. What about theta 1? Theta 1 is 0 because this is the slack bus. What about theta 2? Unknown. Theta 3, unknown. However, once we calculate theta 2 and theta 3, that will actually help us finally to calculate the P1I, P1 injection. We will see that later on. So for the time being, our unknowns are theta 2 and theta 3, N bus minus 1. These two unknowns are there. What about the line data? Now you see we have the sending end bus. So this is the sending end bus. This is the receiving end bus. So sending end bus for line number 1 is 1. Receiving end bus for line number 1 is 2. Similarly, the other two lines have the information about the sending end bus and receiving end bus for line number 2. Sending end bus and receiving end bus for line number 3. The corresponding X in per unit, the line reactances are given. So this is basically X12. This is X23. And this is X13. Okay. And the ratings are given in MVA, line ratings. Okay, so that means these per unit values are calculated based on this base power and their rating, this rating. Okay. So now then, let us calculate the B entries, okay, bus admittance matrix. The B entries, as I said, B entries can be calculated easily calculated by the formula that I have shown. But in the slide, I used actually the Y bus concept. Okay, first I formulated the Y bus matrix, and then I took the entries from the Y bus to form the B bus. But another way to do it, as I just said a few slides ago, I can also formulate it simply directly from this bus, from this entry here. So let us do it here. Let us calculate the entries. So B11, what would be B11? This is bus number 1. Two lines are originating from here. This is X12, X13, and X23. So B11 will be 1 upon this line plus 1 upon this line. These two lines are present. So what are the entries? X12, 0.0576 plus 1 upon 0.092. So whatever value comes, that will be B11. What about B22? B22, which lines are connected? This line and this line. These two are connected, or these are originating from bus number 2. So it will be 1 upon X12 plus 1 upon X23 So simply 1 upon x12 is 0.0576 plus x23. Take this one. Sorry, so x13 stake. So x13 is the last one actually, 0.17. So 0.17. So you calculate this, and whatever value comes, that should be B11. X23 is 0.092. Then you calculate it, whatever comes, that is your B22. B33 with bus number 3, these two lines are connected. So this line is 1 upon x13, this line, and this line is 1 upon x23 plus. So 1 upon x13 is this one, 0.17, x23 is this one, 0.092. When you add them, you calculate them, whatever comes, that is your B33. What about B12? B12 is simply minus 1 upon x12, and that is equal to B21 because of the symmetric nature of the matrix. What about B13? That is minus x13. That should be equal to B31. And what is B23? It is 1 upon minus x23, and that should be equal to B32. So these are the steps. These are the steps that will help you to find out the entries of the B matrix. Okay, so you can check the values of your whatever equations I have shown here. You can check your calculated values with the ones that I have put in the next to next slide, maybe. Yeah, that I have put not here. Okay. So I'm talking about, yeah, these entries, B12. Okay. So you can cross check. You can cross check your entries with the B matrix. Here I have adopted a different approach. Okay, here I have adopted an approach that starts with the formulation of Y bus. You can also follow the step here. You can also follow the step here, no problem. I just demonstrated another method directly using the line data. Okay, so here the method that I just showed, you don't have to formulate the Y bus. Well, ultimately with the formulation of Y bus, you get the entries here. Okay, and using these entries, you can find out the B and then the B dash. So the Y bus shown over here, will be useful if you are following the method shown in slide number 10. Okay, slide number 10. The method shown over here is basically using these values, B11. So here B11, this B11 for this one is simply B12 plus B13. So once you formulate Y bus, you have to take B12 from the Y bus matrix and B13 from the Y bus matrix, along with their signs, to get the B matrix here. So this is the big B matrix. Okay, the big B. So if you follow the Y bus method for getting the B matrix here, so you simply calculate the Y bus first, and using the entries of the Y bus, you find out the entries of the B matrix. So this is another method. Both are correct. Both can be, any of the method can be followed to find out finally this B dash matrix. Remember, B dash matrix is one dimension less than the B matrix. Okay. So in the B matrix, the big B matrix, it would be 3 by 3. B dash matrix will be 2 by 2, n bus minus 1 by n bus minus 1, with the elimination of the swing bus entries. So to reach from here to here, you eliminate the swing bus entries of the B matrix. Swing bus. Okay, and then whatever is left is treated as B dash. So this is the B dash. Once you find the B dash, you take the inverse of B dash. Okay, as I just discussed earlier, how to find theta unknowns using inverse of B dash multiplied by P injection. Okay, so your P injections were already calculated. Okay, P injection 2 P injection at bus 2. So that is P2I. That was shown as P2I. It was 53 megawatt. If you want to take it in per unit, of course, you have to take it in per unit because all these entries are based on per unit line reactances. So here also, these injections should be in per unit. So in per unit, you have to divide by the base MVA, which is 100. P3I, it was minus 90 megawatt. So now it will become per unit, divide by 100 MVA, divided by 100 MVA. So that will give you minus 0.9 per unit. So this is how you get the injection, power injection. This is the reduced B matrix or B dash matrix. You take the inverse of that, multiply with the P injection, and you solve this expression. Solve these two matrices, you multiply them and get the result for theta 2 and theta 3. The result will be in the form of radians. Once you get this theta unknowns, so you have now theta 1, you have the knowledge of theta 1, theta 2, and theta 3. So you have the theta vector as this. Theta 1 is 0, theta 2 is minus 0.0025, theta 3 is 0.0544, all are in radians. So you have the theta, okay, you have the theta vector. Using this theta vector now, we can use this expression of P line flow equals MVA base into the B line into A matrix into theta. So again, what we are doing, simply we are writing P line flow, P line vector. Because of the presence of this 100, this will become megawatt finally. So we can write base MVA, base power, into this is B line. So simply this is 1 upon x12. This is 1 upon x23. This is 1 upon x13. Okay. So that is B line. So this is B line. This is base MVA. This is A matrix. This is theta vector. So this is the explanation of all these 1, 2, 3, 4 entries over here. You solve it, you find out the megawatt line flow through your 3 lines. So that means now you know what is your P12, real power flow from bus 1 to bus 2, P23, real power flow from bus 2 to bus 3, and P13, real power flow from bus 1 to bus 3. With all this information, if I plug these values into the network, given network, so let us see what happens. What happens if we plug these two values, these 3 values actually. So when we plug these values into the network, let me draw the network first. Let me erase this. So yeah, so the network was like this. We had a generator at bus 1, another generator at bus 2. We had a demand here, and this was the 3rd bus with only demand, no generation. So this was bus 1, this was bus 2, this was bus 3. So now we know P12. What is P12? This is P12, 4.3403 between bus 1 and bus 2. What is P23? P23 means it is, so the direction is this. The direction is this from 2 to 3, 57.5002. And what is P13? 32 point from 1 to 3, which is 32.5885. So now we can apply a KCL at this node number 1, and you can find out the power generated by this generator. Because there are no loads, so whatever power is coming out from this bus is going to the remaining part of the network. So if I add this flow out of the bus 1 and this flow out of the bus 1, so I can say P1 injected is simply P12 plus P13. So that means if I add 4.3403 plus 32.5885, which is done here, I will get P injection at bus number 1. And that is the generation of bus generation from the generator at bus number 1. Okay, so now then we can also check for the balance between total generation and the total demand finally. So total generation should be the generation from this bus, which was 63 megawatt. Now this one comes up as 36.9288 megawatt. The demand over here was 10 megawatt. And demand over here was 90 megawatt. So the total demand, P demand summation is 10 plus 90, which is 100. And total generation is 63 plus 36.9288, which is approximately equal to 100 megawatt. So we can see that with the help of DC load flow also, we can have a check in the balance of the equality constraint, that summation of PG should be equal to summation of P demand plus losses. But remember, in the DC load flow problem, there are no losses because we have already no real power losses. Forget about reactive power because we are mostly focused on the real power flow, the DC load flow problem. So we're not focusing on the reactive power flow or reactive power losses by any means. We are only focusing on the real power flow. And at the same time, we know that in the DC load flow problem, there are no P losses. Okay, because our line for all the lines are actually ignored, neglected compared to the X lines. So the equality constraint will become summation of PG equal to summation of P demand, which is approximately satisfied here. This one becomes 99.9288 actually, okay, which is approximately equal to 100 megawatt. Okay, so this is how we can apply the knowledge of DC load flow to get the solution of the real power flow through a network quite easily in a quite straightforward manner. And this is an analytical approach, unlike the AC load flow solution, where the equations are nonlinear in nature and we cannot adopt any analytical way to solve the problem. Rather, we have to use or apply some numerical algorithm like Gauss-Seidel method, and that is time consuming, iterative in nature. On the other hand, the DC load flow is non-iterative, straightforward, linear in nature. These are the advantages, but the disadvantage is that we do not have any information about the bus voltage magnitude deviations, because all bus voltage magnitudes are assumed to be 1 per unit. Second disadvantage, we do not have any information about the Q line, that is the Q flow through the lines. Okay, so these are actually the disadvantages or shortcomings. And because we are approximating, actually we adopted some approximations or some assumptions, simplifying assumptions on the actual formulation of AC load flow to reach at the DC load flow formulation. So we can say easily that this is an approximated result. But in cases where we need very quick solution, an approximate solution is enough for our decision making. In those cases, we can adopt DC load flow. Okay, so thank you very much. And the next class, we will again continue where we actually left. That is, we started actually from the DC OPF slide, and we deviated our discussion from that point because the DC load flow, the knowledge of DC load flow will be required at some portion of the discussion in the DC OPF problem. So that's why during the discussion of the DC OPF, I deviated from that discussion. Now the DC load flow example as well as the DC load flow formulation is complete. So in the next class, the next lecture, we will again go back to the DC OPF slide, and we will start from where we left there. Okay, from the point where we left the DC OPF slide. So, okay, thank you, everyone. See you in the next lecture. Assalamu alaikum.